Hello, welcome to lecture 4. So, we will continue from where we left in the last lecture. We are talking about the applications of RF technology in general and with a focus on what kind of devices are going to be used. So, today we will talk about, we will continue on the discussion, we will see what kind of devices are used. This is just to give you a flavor that these are the different existing or currently used device technologies that are used in all this very important RF application, and those devices are what we are going to study in this course. Okay. For instance, in the last lecture I told you gallium arsenide pseudomorphic HEMT is used in the LNA in a military radar, for instance. So, we are going to talk about, we will not study about MMIC per se because that is more of a circuit design, it is an IC. This course is not about MMIC, but we are going to talk about the discrete devices such as a gallium arsenide HEMT or gallium nitride HEMT, okay, or silicon CMOS for RF. We are going to talk about all of these things in these courses. So, that is why this 3 and lecture 4 are to give you a flavor of those devices that are going to be used in different system. Okay. So, let us come to the whiteboard here. So, let us look inside a smartphone. This is actually an old smartphone, maybe 3G, maybe 10 years back or maybe even more, but you know the basic premise remains the same. Again, you can see that this is a tear down picture of the different components of inside a cell phone, although we are going to look at one particular component here, which is the chip. This is the chip. Can you see this chip? This chip is the chip for GPS, global positioning system, navigation. We all have GPS inside our phone, of course, right? We all know it. It is not a trivial thing, by the way. The GPS chip has to work in low battery condition, extremely bad weather, stormy, rainy, etc., and it should give you very accurate location. You depend on the GPS location is so critical. All your Google Maps, your driving, your food delivery apps, it's a part of our life now. We cannot imagine a cell phone without a GPS, right? Although it was not the norm. People, this was a technology that was developed. So, the GPS chip is inside the cell phone now. Of course, there are many things. For instance, there is a Triquent is a company. Triquent has a power amplifier, which is this, right? There are many power amplifiers. Why? Because they may be operating at different frequency bands, maybe, we do not know exactly, but it just shows that there are different power amplifiers. There is a transceiver. Although the power amplifier should be a part of the transceiver, but this cell phone companies, they may have different nomenclature. So, there is a transceiver which is from Infineon, the power amplifier which is from Triquent. The power amplifier may sit outside the active transceiver because the power amplifier is the most power hungry block. I keep telling you that, right. So, there are many things inside it, but let us see this GPS chip. The GPS chip is very critical, the navigation chip, right, and inside the GPS LNA is again super critical. LNA, because your signal that you are getting from the satellites for global positioning, the navigation, India has its own Navig system, by the way, coming up. So, you need to take a very weak signal with a lot of noise, you need to amplify, you need to get the location very accurately. So, LNA is a very critical component. What kind of transistor goes into making the GPS chip? I mean the LNA of the GPS chip, I am talking only of the LNA, the low noise amplifier. Now, if you look at Infineon PMB2525 Hammerhead 2 GPS in Google, you may not be able to find out what kind of transistor goes in there. The data sheet may not mention that actually, but you can do the reverse. You can go to companies that sell LNA or low noise amplifiers for GPS, and then you find out what device goes in there. So, we can do that. So, I did that. So, see, this is a company called Analog Device. Again, I am not advertising for this company, just that Google is throwing me up this, and there are other companies I am sure that do this. This is a product name. This is a low noise amplifier that is used for GPS, global navigation system, GNSS also. And look at the noise figure, 0.8 dB, it's excellent. 0.8 dB noise figure is excellent, and that is much better than the 2 dB noise figure that we talked about in a military radar. See, because compared to military radar, a GPS needs to be much more sensitive to noise because you are going to pinpoint the location exactly, okay, or maybe this particular GPS is a more recent version than that radar. It could be, I mean I am not going to comment in general about radars LNA versus a GPS of cell phones LNA, okay. I am just telling you that 0.8 dB noise figure is excellent, okay, and the gain is 20 dB, okay. Now, what is the device technology that goes into this low noise amplifier? This is the data sheet. You click on this PDF data sheet, you are going to get a data sheet like this. This is the data sheet of the GPS low noise amplifier that is sold by Analog Device, this company Analog Device, and they will tell you what is this device. You see, this is in GPS Galileo GLONASS system is Maxwell's advanced silicon germanium process. So, this LNA is based on a silicon germanium device technology. What is silicon germanium device? It is an HBT. Silicon germanium is an HBT, no questions asked. HBT stands for heterojunction bipolar transistor. Essentially this has a silicon emitter and a graded silicon germanium base, and then again a silicon emitter, probably a collector, sorry. This is a silicon germanium HBT and it is often used along with a CMOS process. The silicon germanium HBT is fabricated in a CMOS process along with rest of the chip, digital or logic or other things which are CMOS based. So this is called a bi-CMOS process many times, because you have a bipolar device which is a silicon germanium HBT, and that is useful for making things like LNA, correct, and an RF radio frequency domain. It coexists in the same wafer, probably it coexists in the same lot along with digital, logic, memory, other application, other chips which are based on purely CMOS. That is why it is called a bi-CMOS process. We are going to discuss about bi-CMOS in this course. We are going to discuss about silicon germanium HBT in details in this course. This is just to give you a flavor that yes, a GPS, a global navigation system low noise amplifier does use silicon germanium HBT technology today, and we are going to talk about silicon germanium HBTs in this course. These are different data sheets here. Some of these we will probably discuss in the when you talk about these technologies, not always, but some of the device technologies we will go through the data sheet also, just to understand what's basically it means, okay, the silicon germanium. Now let us take a more recent phone, iPhone 12 Pro Max, more recent phone, may not be the latest phone, but it is still a very recent phone. This is the I guess the back side. There are also back PCB, front PCB. There are so many components here, and one interesting thing is that if you take up any of this and you Google search, you may not exactly find that component. It's not explicitly listed and mentioned and detailed out by the vendors that supply this to these phone companies. It's very difficult to find the exact component number in Google, and you find out it's very difficult. Okay, I have done that a lot. It's very difficult because the details of this particular component or the chip may not be publicly available. Okay, that's what I have come to the realization. So for instance, let's take a look at some of these components. Avago is a company, it makes the front end module, and this is 8200 front end module, this is your front end module. So front end module sits beside the antenna and the mixer. I told you front end module, remember, it could have the low noise amplifier, power amplifier, okay, and it could have the switches, that is a front end module. Then there is a transceiver, although the front end module is a part of transceiver, but in this case Apple has chosen to have them separate, maybe, or at least the people who are tearing down this and showing it, they are identifying it as a transceiver. There are actually many transceivers. There is one transceiver here, there is one transceiver here, because they may be of different frequency bands. This is sub 6 gigahertz transceiver, that could be a different frequency range, intermediate frequency range transceiver, okay. So depending on the frequencies they may have different transceiver. This transceiver is made by Qualcomm. What is the device technology that is going behind this transceiver? Okay, transmit receive, this is an RF part by the way. And what is that device technology going in this front end module? This we need to know that, it's important. Then there is a company called Skyworks, very famous company, that is also making front end module. Maybe these front end modules are for different frequency ranges, for different applications, we don't know exactly. We are seeing this image of the inside of the iPhone. So what about Skyworks 58240 front end module? Again, it's very difficult to find that exact part, but you can find a close enough part. You can go in the internet and find out what is a close enough part to that Skyworks component, and you can see that, oh, if this Skyworks component has this device technology, most likely this different Skyworks component that you have here, this is another Skyworks, might also use a similar device technology. We want to understand what device technologies go in there, that's all, right. So let me first take maybe the Qualcomm transceiver. So you see this 865, its SD stands for Snapdragon. Snapdragon has a processor, of course, but Snapdragon RF transceiver is built into that processor. So you see the 865 is a advanced 5G chipset. It supports sub 6 gigahertz 5G, even millimeter wave. That means it can probably go up to 28 to 30 gigahertz also. Spectrum sharing, so many things are there, okay. It's an RF transceiver, and it is made on a single chip 14 nanometer node, that's all. This 14 nanometer tells you that it is a node, and when it is a node, it means it is a CMOS node, which means this transceiver is made on a 14 nanometer CMOS node, end of story. Now CMOS may not be the exactly technically correct word, at 14 nanometer. At 14 nanometer you are going to have like a tri-gate, or people call it also FinFET. It is like a gate all around CMOS. So, it is not like a bulk planar CMOS. You have like a channel between, this is source, there is a drain here. Okay, the gate wraps around the channel from 3 sides. It is called a tri-gate or a FinFET. We are going to talk about tri-gate FinFET RF devices in this course also. We will talk about RF CMOS device because that is what is historically and that is what is even today very widely used, but because CMOS used to refer to the planar form, and after 45 nanometer, I believe after 32 nanometer people have increasingly migrated towards this tri-gate, especially at 22 nanometer. At 22 nanometer and below it is definitely tri-gate. So, tri-gate architecture is being used in the RF, this is your transceiver. Now, here is one thing you have to keep in mind, this 14 nanometer, 22 nanometer nodes are actually optimized, developed for digital processing application, maybe memory, logic. Those are the most dominant pressing application, the digital logic of course. RF designers also use that platform to design an RF transceiver. So, in oftentimes, not always, oftentimes this is not specifically, the platform is not specifically designed for RF, it is designed for digital, but you are going to implement your RF transceiver, your RF switches, maybe your all these kinds of baseband modulation, intermediate frequency filtering and amplifier etc. are implemented on this digital platform. We call it the RF on the digital platform. Okay. But there are also specific RF platforms that are designed as a slightly more expensive, that are designed for RF, such as RF SOI, silicon on insulator. There is a silicon, below that there is an oxide layer, and below that there is a silicon. So, you are basically trying to create this, you are trying to reduce the crosstalk and the coupling to the substrate, because the silicon substrate is very lossy at RF frequencies. You want to minimize that loss. So, you have an oxide, a buried oxide layer to prevent that coupling, and then that oxide may have a trap rich layer to trap all these defects and all these carriers from dangling bonds etc. So, RF SOI may be slightly more expensive, but it is designed for high performance RF devices, and RF SOI kind of can compete with even gallium arsenide technologies as far as noise is concerned, for instance. Okay, noise linearities are concerned. But anyways, this is a Qualcomm transceiver IC that goes there. Skyworks has the front end module, and front end module has a power amplifier. Let us look at Skyworks power amplifier. The Skyworks 65006, this may not be the exact component that is here, but you can see it is a similar family of components, because you may not be able to find, at least I could not find this exact component detail in the internet. Okay. I had to go from one to another, on to another, and I found out the Skyworks 6500 is a power amplifier. Yes, it is a power amplifier that goes in the front end module. And what is this power amplifier? This goes in 2.4 to 2.5 gigahertz operation, but what is the device technology? The device technology is indium gallium phosphide. Can you see that? Indium gallium phosphide power amplifier. What is this indium gallium phosphide transistor? Is it a field effect transistor? No, it is not a field effect transistor. It is a heterojunction bipole. This is from the data sheet, okay, Skyworks. HBT, just like silicon germanium, you have compound semiconductor indium gallium phosphide HBT used in a Skyworks power amplifier that goes into your iPhone 12 Pro Max most likely. So, I told you the power amplifier in your cell phone has to be a compound semiconductor 35 HBT. For the efficiency it gives, the power handling, the knee voltage, the operating voltage, everything included, this is the best. You cannot have a silicon device there, it is an indium gallium phosphide. So, indium gallium phosphide, this technology is built on the substrate which is gallium arsenide. That is why it is called a gallium arsenide. There could be also indium phosphide substrate that is little bit more expensive. People might use it for maybe military, strategic, where cost may not be so much of a matter, but in things like this, of course in an iPhone also cost should not matter as much, of course, but indium phosphide is more high performance, it is more niche, okay, sub terahertz, it can go up to almost terahertz. So, that is a different, but gallium arsenide substrate is well enough to make an indium gallium phosphide. So, there are many layers, emitter might be a stack of layers, then base, then collector, sub collector, all these things are built on a gallium arsenide platform, and the top emitter could be the indium gallium phosphide emitter of course the topmost part will still be N++ gallium arsenide or something to make a low contact, okay, to the emitter, but indium gallium phosphide heterojunction bipolar transistor is used in this power amplifier that goes in an iPhone 12 Pro Max that we found out here. You see, Skyworks is supplying that front end module. The front end module has the power amplifier, right? The front end module has the power amplifier in the transmitting chain, correct? This, you know, in a cell phone your supply voltage will be probably around 3 volt, 3.3 volt, which means you need to get power out in this power amplifier at less than 3 volt or 3 volt max, which means if you have an ID, you know, characteristics, your knee voltage must be much lower than 3 volt, because at 3 volt you need to get power out. So the swing should be such that your knee voltage should be as close to 0 as possible, and HBT gives you a knee voltage that is less than 1, you know, 0.5, 0.7 volt. That's exceptionally good. It's very, very low. You need a very low knee voltage, okay, because your drain voltage itself is very low. It's not like you have 28 volt. In a cell phone you just have 3.3 volt, right. Avego, there is an Avego front end module also. What does Avego use? Avego front end module also has a Broadcom power amplifier, and you can see that this power amplifier is going to use what? It is not written here, you see. Okay, it is written here. It again is an indium gallium phosphide HBT. It is an MMIC tech. They have gone one step ahead and also mentioned that it is a MMIC technology. It is a micro monolithic technology, and this is used in the particular phone amplifier. Okay, we got a feeling for that now, right. Now if I do a technology wise partitioning of this inside of the cell phone, this is a cell phone, a smartphone, handheld gadget, and this need not be universal. Different companies could have different shifts to it, but all the digital logic, memory processing, everything is on CMOS, of course, no questions asked, everybody knows that. But the RF part, where you are going to have this transmit receive chain, you can call it the front end module, you can call it a part of the transceiver, is predominantly silicon germanium BiCMOS process. It is BiCMOS because there is CMOS coexisting together. See, silicon germanium can be fabricated in a CMOS line, and it is very much CMOS compatible, and what happens is that you make the integration so much easier compared to having 3-5 semiconductor. Integration is a very, very important concept. Can you integrate everything, every functionalities together? So with if you do it on silicon, you have a better chance or better shot at integrating technologies together, although you still use different chips. See, this is a different chip, this is a different chip, this is a different chip, the power management IC, and the power amplifier is a different chip. You still have so many different chips. It is very, very, very unlikely to bring all of them together in a single chip, because you cannot make the power amplifier on a silicon. It will be not as efficient. Your cell phone battery has to be the size of a huge brick, okay, if you use a silicon device. I mean, so you need to use a compound semiconductor power amplifier. Similarly, silicon germanium BiCMOS is used for this receive and transmit chain. Why? Because for a given node, for instance, I have a 130 nanometer CMOS node. If I use CMOS, the kind of cutoff frequencies that I will get, FT and Fmax, those are cutoff frequencies. You know, they are like the maximum frequency at which you have gain of 1. Okay. So those cutoff frequencies, you have certain value. Now you need a certain value of cutoff frequency which is not achievable by 130 nanometer. You have to go to a more aggressively scaled node such as 90 nanometer. Your cost will increase enormously when you go to a higher node. The foundry will give you a 90 nanometer node, but they will say ki, you know, the price is much higher, of course. However, if you use silicon germanium, at 130 nanometer, you can easily meet the cutoff frequencies or other parameters which are achievable using a 90 nanometer CMOS. A 90 nanometer CMOS will give you the same cutoff frequencies or other RF performance parameters as a 130 nanometer silicon germanium, because the silicon germanium is inherently superior to CMOS, silicon MOSFET, as far as cutoff frequencies are concerned, as far as gain is concerned. So BiCMOS gives you the advantage of both CMOS and bipolar device. Silicon germanium gives you advantage in cutoff frequencies, in gain over CMOS, it gives you much better, but it is not as good as static power consumption is high in BiCMOS, I mean in silicon germanium, because it is a BJT, it is an HBT. So you use CMOS where the static power consumption is much lower, integration is much better, you have large scale manufacturability, planar process, etc., etc. So CMOS and BiCMOS, I mean the bipolar device, combined to give you BiCMOS. So that is used in the RF chain, and of course do not quote me wrong, there are cell phone companies that might use still this used as a CMOS, but the dominant trend is it's silicon germanium BiCMOS. The power amplifier is actually not gallium arsenide LDMOS, it's as I told you, it's a 3-5 compound semiconductor HBT, gallium arsenide indium gallium phosphide HBT. today's technology. Okay. Then cellular infrastructure, when I say cellular infrastructure, I mean to talk about the base station, the nearest base station in your locality. What is the LNA used there? LNA for wireless infrastructure is basically cell phone tower, cell phone base station. You see, this is a company, NXP, very famous company. Again, I am not advertising for that, just happened to pick it up from Google. There are other companies also that sell. I am just picking up 2 examples here. This is one example of a low noise amplifier that goes into cell phone base station or tower. This is another technology that goes into cell phone base station tower. You can see here this is mentioned EPHEMT. E stands for enhancement mode. Enhancement mode, okay, enhancement mode is called E. What is enhancement mode? Enhancement mode is a device whose threshold voltage is positive. It's like a silicon MOSFET. It means to turn on the device, you need to apply a positive voltage on the gate. The contradictory device is depletion mode, where you have to apply a negative voltage on the gate to turn the device off. So, all compound semiconductor devices 3-5 such as gallium arsenide, MESFET, HEMT, gallium nitride, they are inherently D mode. Their threshold voltage is negative. Silicon MOSFET is enhancement mode because the threshold voltage is positive. So, E mode gallium arsenide, it's E mode HEMT, it's a gallium arsenide HEMT by the way, is a very interesting concept because you are making a compound semiconductor device E mode. So, this technology is a gallium arsenide HEMT technology, pHEMT, pseudomorphic HEMT, but this is enhancement mode technology. Okay. We will talk about gallium arsenide pseudomorphic HEMT in our course as I told you, and it gives you 24 dBm maybe output power, 15.9 dB or 16 dB gain, etc. So, this is used in wireless infrastructure gallium arsenide, but this is also used. Now, what is this? If I do a Google search, I may not exactly find that, but I know this family of devices or low noise amplifiers are available. So, this is the family of amplifier, low noise amplifier, which is also sold under the name of this by the same NXP. This website is from NXP only, and it tells you what is this made of. This is made of silicon germanium. So, silicon germanium bipolar technology is used in cell phone towers as well as in radars as well as in maybe cell phones, whereas gallium arsenide based HBTs HBTs are used in power amplifiers in your handphone. In the cell phone base station, the base station tower LNA, low noise amplifier, people also use gallium arsenide HEMT. Please remember that. Okay, they also use gallium arsenide HEMTs. Okay. Now, what about power amplifier? In cell phone power amplifier, I told you this is from a company. You can see power amplifier wars begin. This is from 2020, few years back. Okay, what is the status? The status is people use a combination of both. When I say both, there is silicon LDMOS. LDMOS is like a big brother of MOSFET. You can say it's a big powerful brother of MOSFET. It's for high voltage RF as well as high voltage for power switching. So, in this case it is a high voltage RF LDMOS versus gallium nitride device. These two technologies are competing for the cell phone base station power amplifier, where you have to boost the signal and send a large amount of power out. Okay. This is a very important battle by the way. They are at 3.5 gigahertz or below. The silicon LDMOS has cost advantage, performance advantage also, it's neck to neck, but at something like say sub 6 gigahertz, when I say sub 6 gigahertz, 4.5, 5 gigahertz, etc., LDMOS kind of loses out to gallium nitride. Gallium nitride gives you very good power performance, efficiency, gain, etc., at a much smaller device footprint. Okay, so gallium nitride can give significant advantages over LDMOS, and we will exactly talk about that in that course also. In this course, we will talk about gallium nitride versus LDMOS. We will show these discussions. We will talk about the data sheet from a gallium nitride device. Okay, we'll go through these things in different modules in this course by the way. Okay. So, again NXP is another this company I told you. This is from 2023 June. This is very recent. You see, they rolled out a gallium nitride RF power amplifier for the cell phone station, and they have a cooling on the top to reduce the weight by 20%. They are cooling the gallium nitride power amplifiers from the top side to take the heat away, because this cooling is a very important aspect. Okay, and they are combining both LDMOS and GaN. They are not saying that we are only going with GaN. They have both LDMOS and GaN. Okay, these are some numbers. To appreciate these numbers, you have to be in this area and work so that you can get an appreciation of these numbers. But these are for 3.3 to 3.8 gigahertz. See, the LDMOS acts as the driver. What is the driver? You have a power amplifier. Suppose the power amplifier has a gain of 15 dB. that is the gain of the power amplifier, and the output you need suppose 40 dBm of power. Suppose I am telling you what is 40 dBm. 40 dBm is basically 10 watt. That is your output power you need. I am just giving an example. Okay, 40 dBm of power you need at the output. Your gain of the device is 15 dB. So that means at the input you need to give 25 dBm of input power. So 25 dBm of input power with 15 dB gain gives you 40 dBm of output power. Power is always expressed in dBm in this RF world, and we always talk about power. We don't talk about voltages and currents here. It's power. Okay, so 25 dBm. How much is 25 dBm? So 20 dBm is 100 milliwatt, and 30 dBm is 1 watt. So this 25 dBm is between 100 milliwatt and 1 watt. It could be few hundred milliwatt. So few hundred milliwatt has to be given in the input, and the output will be 10 watt. That is your power amplifier. But you may not have a source that supplies a few hundred milliwatt of power here. Okay, so you need what is called a driver amplifier. This driver amplifier will have its own gain. Suppose the driver amplifier has a gain of 10 dB, which means to get 25 dB to the power amplifier with a driver amplifier of 10 dB, at the input of the driver amplifier I just need to have 15 dBm of power. If I put 15 dBm of input power to the driver amplifier with a 10 dB gain, it will bring that level up to 25 dBm, and that 25 dBm is now fed into the power amplifier to get up to 40 dBm. So this 15 dBm is how much? 10 dBm is 10 milliwatt. So 15 dBm will be few tens of milliwatt, maybe 20-30 milliwatt, something like that. Now that could be available. So 20-30 milliwatt of power is put into a driver amplifier that is boosting it up to few hundred milliwatt, that is in turn fed into a power amplifier that is boosting into 10 watt. This is how it works actually. This is it's a two stage, for instance, or maybe it's a driver amplifier is here. Okay, so that LDMOS is used as a driver amplifier, and the GaN plays the role of the secondary power stage, giving signals a final push. So the power amplifier might be made of gallium nitride. Maybe there are two stages of power amplifier, not one stage but two stage. The second stage is of gallium nitride. So it could be something like that. So this is just to tell you that gallium nitride LDMOS are now coexisting, but gallium nitride is also it's coming up with better and better solutions for this wireless cell phone applications. Okay, that is not to say that gallium arsenide is out of business in cellular base station or cell phone tower application. In all the RF electronics, gallium arsenide is very much there. This is again from NXP. Gallium arsenide MMIC, again MMIC is the microwave monolithic. They are this is for 3G 4G, so maybe few years old, but even in 5G, okay, they are very much used as, for instance, the intermediate frequency amplifiers. You have the signal, you mix the signal, and then you get this intermediate frequencies, low frequency, you have to amplify that, you have to filter that, etc. So intermediate frequency amplifier. Driver amplifier may have another pre-driver, by the way. Okay, it is a pre-driver. So pre-driver, buffer amplifier, low noise amplifier in the receiver front end, all these things are also being implemented in gallium arsenide technology in the cell phone station, base station or tower. Okay, so just don't get me wrong that it is only LDMOS or gallium nitride, that is for power amplifier, but the other components, mixers, VCOs, low noise amplifiers, switches, buffer amplifiers, etc. gallium arsenide is very much in the race. So is silicon germanium. Okay, so is RF CMOS. All these are competing technologies. Market will decide which company will, the company will decide based on the market and the time to market, the cost and the user base, etc., which technology to choose from. But in this course we are going to talk about these different device technologies, the device concepts, the device know-how. Okay, so with that we are at the end of lecture 4. So thank you for your time in walking through these slides with me. In lecture 5 we will start from some of the recap of the basics, and then we will build on the diodes first, the 2 terminal varactors, Schottky multiplier, impact diode, gun diode, etc., which are also very useful, maybe I have not mentioned in today's lecture. Then we will transition to transistors, 3-5 transistors, silicon transistors, gallium nitride, bipolar transistors, and some concepts in microwave engineering, okay, and passives. That is how we are building this course. Okay. So thanks for your time. I hope to see you in lecture 5. Thank you.